Right now, as you watch this, the nearest exoplanet around the nearest star is about 4.24 light-years away. And even at 20% the speed of light, a probe would still take roughly 21 years just to arrive. What if I told you the biggest problem isn't building a fast ship? It's arriving with enough fuel to slow down, surviving interstellar dust, and still phoning home? Stay with me, because by the end of this video, you'll understand the real roadmap to exoplanets and why 2026-era astronomy is forcing engineers to finally treat interstellar travel like a technical project, not a fantasy. This is where your intuition breaks. The speed of light is 299,792,458 million-s, and our fastest spacecraft are nowhere near that. But the impossible facts are piling up. The nearest star is still 4.24 light-years away. At 0.1 c, the trip is still 40-plus years one way, and the energy to accelerate anything to a meaningful fraction of c becomes so huge that the fuel problem stops being an engineering detail and becomes the entire mission. So the question scientists are seriously asking now isn't, can we go? It's, what's the first exoplanet mission that doesn't die on the way and still returns data? To get why this is so hard, you need the normal physics. First, rockets. Chemical rockets don't scale to stars because of the rocket equation. If you want more speed, you need exponentially more propellant. That's great for reaching orbit and exploring the solar system. It's brutal for interstellar travel. Even improvements like nuclear thermal or electric propulsion help, but they don't magically erase the math. Second, distance. Interstellar space isn't empty. It's thin, but at 0.1 c, a dust grain is like a bullet. So you either need serious shielding, or you need to be tiny. This is where things get strange, because the most realistic first exoplanet mission might not be a giant starship. It might be the opposite, a swarm of ultralight probes going very fast, accepting that some will fail, and winning by numbers. And that sets up the real interstellar checklist. Stay with me here. Acceleration. How do you reach high speed? Survival. How do you handle dust, radiation, and reliability for decades? Deceleration. Arriving is easy. Stopping is the nightmare. Keep this open loop. The secret reason most interstellar concepts fail isn't that they can't go fast. It's that they can't stop. Subscribe if you want space tech explained like an engineering roadmap, because what I'm about to lay out is the three-path future: laser sails, nuclear fusion, and gravity or braking tricks, and which one has the best shot at becoming humanity's first true exoplanet mission. Now let's tell the story like detectives, because the future of exoplanet travel is really a chain of discoveries. Back in 1903, Konstantin Tsiolkovsky formalized the rocket equation, the first warning that fuel becomes your prison. In the 1970s, Project Daedalus, a British Interplanetary Society study, explored fusion-driven interstellar probes. It was never built, but it shaped how serious engineers think about interstellar missions. You need ridiculous energy density, long-duration reliability, and a plan for decades. Then in 2016, breakthrough Starship proposed something wild but strangely practical: gram-scale probes pushed by ground-based lasers to about 0.2 c. The genius move is that it dodges the rocket equation by not carrying fuel. The engine stays at home, and the spacecraft is basically a sail. Now fast forward to the mid-2020s into the 2026 era. The reason this conversation is heating up is that astronomy is handing engineers a better map. Exoplanet catalogs keep growing, and telescope observations, especially of atmospheres, are upgrading the target list. Instead of some star somewhere, we can point to nearby worlds and say that one is worth chasing. The moment you have a real destination list, the question stops being, wouldn't it be cool, and becomes, what architecture gets us there first? Here's the core explanation. The future of exoplanet travel likely splits into three paths, and they're not equal. Path 3 is the big ship path, advanced nuclear concepts, and in the far future, fusion. This is the dream of bringing real shielding, real instruments, and a robust payload to another star, enough to do deep science for a long time. The trade-off is obvious: development time and engineering scale. It's hard, expensive, and slow to mature. Path 2 is the tiny and fast path: laser sails. Laser sails are one of the most realistic ways to reach a significant fraction of light speed without hauling fuel. It's like windsurfing, except the wind is a laser beam. The spacecraft can be grams, the sail can be meters across, and the mission can launch many probes. Some will be lost. That's expected. You win by redundancy and statistics, a very 2026 mindset. Path 1, the path most likely to work first, is the brutally honest path: fast flybys. The first missions probably won't stop. They'll scream through the target system and grab data in a high-speed burst. And here's the secret: interstellar travel has a double energy problem. You need energy to speed up, and then almost the same order of energy to slow down. If you can't decelerate, you fly through the target system in hours. That means your science has to be built for a drive-by. Imaging, spectra, fields, particles, fast, then a long, slow data return over years. That's satisfying because it's real. But it opens new questions. How do you protect a wafer probe at 0.2 C? How do you aim across light years? And how do you transmit a signal back from another star with a tiny power budget? Just when you think you've got the roadmap, here comes the twist. The bottleneck might not be propulsion, it might be communication and survival. At relativistic-ish speeds, even tiny particles can do serious damage. Shielding adds mass. Mass lowers speed. It's a trap. Then communication. An exoplanet probe is insanely far away. The signal arrives years later, and it's weak. So you need extreme pointing accuracy, clever compression, and probably a network of powerful receivers on Earth. And there's real controversy here. Scientists disagree on what counts as an exoplanet mission. Some argue that a wafer-scale flyby would be revolutionary, our first direct close-up data from another star system. Others argue it's scientifically thin unless you can break and do long-term observation. That debate shapes what gets built. That's also why you keep hearing about deceleration tricks. Magnetic sails that push against stellar wind, using a star's light for photon braking, or even futuristic ideas where the destination system helps capture the probe. None are easy, but this is where research is heading, because arriving isn't the same as exploring. I genuinely want to know what you think. If humanity reaches an exoplanet first, how do we do it? A. Laser sail flyby swarm. B. Fusion, nuclear interstellar probe. C. Something unexpected, like a braking trick or staged relays. Comment A, B, or C, and tell me what you'd want the probe to measure first: photos, atmosphere, or signs of life. Because this matters beyond the wow. Exoplanet travel is a forcing function. It pushes power systems, materials, autonomy, miniaturized instruments, and deep space communication, technology that spills back into everything from Earth observation to outer solar system missions. It also changes how we think about progress. If your probe takes 20 years to arrive and 4+ years for the signal to return, you're building science on patience. You're building missions that outlive news cycles. And in the 2026 era, with exoplanet targets getting sharper and more meaningful, the pressure increases. The universe is giving us destinations worth chasing. The hopeful part is this: we don't need warp drives to begin. The first steps are already clear: better target selection, better miniaturization, better beamed power experiments, better deep space communications. Interstellar travel starts as a ladder of practical upgrades, not a single miracle. But this isn't the only wild frontier. Next, we'll break down how a laser sail would actually survive acceleration, the smartest braking concepts that might let a probe stop at another star, and the top exoplanets we should aim for first. Subscribe so you don't miss it. Thanks for watching. The future of exoplanet travel isn't one ship. It's a ladder of technologies, each step making the next one possible. Stay curious, and see you in the next one.